aren't U.S. citizens.
Yeah.
Actually, no. A lot of those guys graduated because we had like I don't want to say like the majority, but we had like 3 or 4 people from India who were all in the same group, and it was just so I don't know. We went when we went out to like lunch as like a group. He took us passage to India because they all said it was the best Indian restaurant around. I hate curry, but man, that food was good. They had these like fried chicken. It was really good. Like it was spicy.
You're gonna make me hungry.
Yeah, me too.
How is your week going?
Good.
It's going.
Did you adjusted your driving skills? No one.
I live on campus, so I live on campus, so I just walk.
What do you prefer first, entertainment or hard work?
Entertaining.
Me too. So the actual lecture material will be maybe 10-15 minutes, and most will be entertainment. So I'll just briefly tell what will be the lecture material, so that if I take all the time for entertainment, so that you do not feel uncomfortable. So, what we are doing in the lecture? Predicting future for interatomic distances, which can be quantized. We got the eigenstates, and we look forward to predict how the work of Isaiah will work in the pen and paper. If one creates some non-equilibrium superposition of eigenstates, how will it evolve in time? We are heavily using shortcuts. One of the shortcuts is annihilation operator, and we are continuing this shortcut. We are going. Last time we got the ground state energy through Hamiltonian in matrix form, right? And today, if time allows, we are, well, it was planned for last time. We are going to get eigenstates of annihilation operator. So annihilation operator is not Hamiltonian, it's not Hermitian, it's not an observable, but it is a very useful shortcut that will help us to duplicate results shown by Isaiah in the last Friday presentations by writing pen and paper. So applying annihilation operator to unknown wave function and seeing what will happen. And we will do it not in the wave functions in continuous coordinate distribution, but wave functions in discrete form. Okay? So please give me some warning about 10 minutes before we end, so that I have time to give something about this class material, because we need to progress. So we are about 70% of the course material, and we will do election day, another election day, not the one yesterday, in the class. So not today, later on I will announce it, so when it will be bigger quorum. So the question will be, would majority prefer standard exam with problem solving or presentations based on projects? So you will have a chance to vote, but I anticipate that majority will be for projects. And it's time to start thinking about projects and preparing to them. So the plan is that it will be an option to replace exam, to give substantial credit that will bring you to high orbit in the sense of grade, by completing mini research and reporting in form of written report and presentations. So it is the hardest part of the class, if you go this way, for me and for you, how to select which projects to follow. If you do not care and you want me to choose, it's hard for me. If you do care and you want to choose it, it's also hard. Because, of course, you're welcome to research anything you like, but it should be connected to the skills that we got in class or in the lab. And we are not yet emperors of universe. We do not have all tools to solve any problem. So it should be something that can be reduced to one-dimensional wave packet propagation, which is, it's very generous. A lot of problems can be done this way, but there are some limitations. So we are approaching the stage of true creativity. So prepare to be super creative, maybe during next coming weekend. By the way, what is going on Monday?
There's no school.
Huh?
There's no school.
Oh, I'm happy with this. But what's the reason?
Veterans Day.
Oh, okay.
Veterans Day is on Sunday. No, but it's
Oh,
observed
it's
on Monday.
observed Veterans.
Okay. So, good. So, you know, some people can think on the background, like while sleeping or relaxing or observing some events. So I'm going to put some seeds into your background thinking, so that next week, maybe even this Friday, but next week for sure, everyone will need to select the project, and on next Wednesday it is the latest time to start the project in the labs. So this is the homework that is okay to bring on Wednesday, but if someone is ready, it will be rewarded. And I looked through and got an idea that the largest credit problem could be challenging. So we'll try maybe to cover it in today's lab briefly, but if you are not attending the lab, here is answer for 2 out of 4 questions in this section. So it's not sufficient for full credit, but at least you can check yourself what should be the answer. So, you know, if you commute position of momentum, the answer is proportional to Planck constant. If you commute accretion and annihilation, it will be just 1. And if you swap their order, the sign of the commutator changes. So in the slides that Kevin was trying to show, but because of time pressure, there was no chance to show everything. You were showing general properties of commutators, and it is one of them. If you swap the order before doing of things that you put in commutation, the results flips the same. So a little less pleasant thing, but we will need to bring 2 homeworks on next Wednesday. Otherwise, we will not match the material. This one will be just running. Isaiah can be excused for this because he already did it as his presentation. So basically reproducing what he did with a little bit more analysis. So running the wave packet code for harmonic oscillator and explore what would happen if one would put the initial wave packet right above the equilibrium, which supports, prompts that there should be no motion. The question, will be there any motion if you start right where the ground state should be? And so momentum is 0, initial position is corresponding to equilibrium, but there is one more degree of freedom is width. So you do some mini research if the width will be very large or very small, and how the dynamics will follow this change in the initial conditions. In the homework that you have submitted, recently. This was the part of the last question. Some of you have excellently answered it, but now we can look this a little bit more details. So shouldn't be challenging. Okay. And if you have no idea how to change potential for harmonic oscillator, you can either use this E equals this stuff, x minus equilibrium squared, right? So it's quite simple. If this equation is too hard, you have a certified helper, expert in harmonic oscillators and well. So, projects. Last year, everyone voted for projects instead. And here is the recording of how they went. So, of course, it will be strange if someone selects exactly the same project as was last year. This assumed to be something different. But general ideas, I'm going to give an overview of general directions. And with your interest, scientific fantasy, curiosity, you can select what, and your knowledge what is possible and what is not possible, you can start developing ideas. So, in the wave packet code, the main thing that you are able to change is the potential, right? And you can put there any function. It can be an analytical function expressed through like sines, cosines, exponentials, or one can make it chopped function of segments, whatever works better for realistic system. So some of you are taking analytical chemistry. Right? Some of you may even do research in analytical chemistry, and you know that there is a technique of electrochemistry when you scan the voltage and see the response, and you get information about ability for accept or to get reduced or oxidized, which energy is needed for like, affinity and ionization energy, right? So if one wants to model it in with the method of code, it means that the molecule that sits on the solvent or in the vicinity of the contact experiences voltage, which means additional electric field. Electric field means the whole potential, which can be like chopped to segments, like to dips. If one apply voltage, it means one adds straight line. Wherever it gets deeper, it's where the electric field pushes electrons to go to. So by changing slope of this additional potential, it means the change of the voltage in the electrochemical cell. So some of you are moving from chemistry to polymers. So polymers can be just as a material for mechanical properties, like polyethylene back in the grocery store, or there could be so-called conjugated polymers, which semiconductors. Like remember when talking about particle in the box, we were speaking about oligomers. So conjugated polymers conduct electricity. Sometimes one needs to photoexcite them, but they are able. But their example, if there is a conjugated alternating bond, it will be able to conduct electricity because this double and single can alternate and move as a wave. So the conjugated polymers are cheap and nice to replace solid state microelectronics, to make everything out of carbons, plastic. But one of the challenges that they are not as solid, strong, and crystalline. There are a lot of defects. So if one makes, for example, a wire out of this conjugated polymers, they will have a lot of defects, which means that randomly there will be some trap states which will catch the traveling wave. So one can have a straight line with several dips that will catch the wave as it goes through. One of the simplest problems, but it's still scientifically valuable. I will give more options than amount of people in the class. It doesn't mean that you need to take one of this. You can take one of this, but not each of them. So in your coming addition to homework about harmonic oscillator, in the work of our champion of quantum oscillations, so in everything we did before, there was only one Gaussian wave packet at initial stage, right? But there is no theorem that initial wave function needs to have one maximum, needs to be one Gaussian. What if we add together two Gaussians, normalize them, and we can add momentum for them to move in the opposite direction and place them in harmonic potential? What will happen? It will be some fun picture if someone does it. It will be related to Schrödinger cat, and it will be related to quantum information processing. Very common problem for chemists is, and I may forget because I'm rushing to complete it in several limited minutes, but by going from one to another problem, we're not actually doing them, we're just considering what can be done. The potential can be either for electron or for interatomic distances or for something else. So the nature of the particle, quantum particle that is moving, may be different as we go through. And there is a piece of information that I didn't introduce, but we'll try to. When we are going from electrons to nuclei, one of the changes of the code that one needs to change the mass. In atomic units, mass of electron is 1, mass of proton is 1836, about 2000, and if one gets for carbons, it will be more than that. So with bigger mass, it will be different time scale. Just being clear. So if one is looking onto chemical reactions, so there is a substantial amount of chemical reactions can be represented in form of one-dimensional potentials, like reactant, barrier, product, right? And one of the ways to represent reactions is either to through this chopped piecewise potential with straight lines in one region, in other region, and barrier, or make a continuous function. If someone selects for such problem, one would need to read or consult with experts in appropriate problem and design parameters for width of the barrier and for height of the barrier and mass of your wave package. And then it can be really connected to real life. So if any of you decide to watch through last year presentations, this is more academic. It was selected by Braden Wade, but I think it is not forbidden to try it once again. So the problem is, what if we have harmonic potential, but we want to model basic infrared spectroscopy, which means interatomic bond is getting distorted by external electric field which oscillates. Oscillating electric field, which means changing slope, and as a result, the potential will move forward and backward. So how the motion of the potential will result onto motion of wave packet. Supposingly, if you look, say, from lower energy to higher energy. If you like something from the projects, make, well, these slides will be distributed, but you may make no, oh yes, I want to do this. Never this problem. So, there will be, in about 2 weeks, I'm going to give a quick heads up to the most complicated part of this course, most complicated material. And there will be a way to include this challenging material into your research. Some of you may say that. So there is a very large amount of chemical problems when the reaction is happening simultaneously in several degrees of freedom. Right? It isn't surprising. It's natural. Like even motion of classical particle can move simultaneously in x and y, right? Several degrees of freedom. But in chemistry, there could be reactions with simultaneous change in both nuclear and electronic degrees of freedom, when wave function and positions are changing simultaneously. And this is the biggest challenge, simultaneous change of electronic and nuclear degrees of freedom. One of examples of such problems is so-called electron transfer, charge transfer. Also not a big challenging words, right? But if you have donor and acceptor molecules that experience jump of, let's say, electron, oxidizing one, reducing another one, it is change of electronic state, right? But at the same time, after electron jumps from donor to acceptor, interatomic distances start to change. So there will be, if a molecule experiences electron transfer, there is a simultaneous jump from one electronic state and another electronic state, and simultaneous change of the interatomic distances. And this problem is typically represented by two crossing potentials. So it is, right now, it's a very big surprise. Before, we always had one potential, right? But it could be two potentials, and wave packet can coexist in both of them, can jump from one to another. Rudolf Marcus got Nobel Prize for just describing these opportunities in 50s, and the prize was given like in 90s. But it is accepted part of chemistry. And there are several examples of where these crossing potentials are implemented. One of the, how long we do this time? So about 10 minutes for this stuff and then for watching TV, right? So one of the examples, if you have metal organic complex or metal doping into crystal, right? Anyone took inorganic? Not yet? Okay, then this pleasure is in your future. There are so-called states, transitions of, have you ever seen these abbreviations? At least one. What do they mean?
Ligand to metal charge transfer and metal to ligand charge transfer.
So there is, if there is a metal and organic ligands around, charge may go from metal to ligands or from ligand to metal. And for each of them, interatomic distance will simultaneously shrink, contract, or expand. So it is when there is no charge transfer and there is charge transfer, and then this is interatomic, average interatomic distance. There are several graduate students and postdocs who will be happy to assist you in your projects. So after you select project, there could be a helper assigned. One of the helpers is doing this metal to ligand to metal charge transfer. in semiconductor perovskite conductor with manganese doping, and so here is the electronic orbitals on the metal, and somewhere here there are the ligands surrounding atoms. Did you took our Bow principle in your undergraduates? Oh, you never pronounced it. Did you, so it's German word for building. Build on, Aufbau, how you populate orbitals of an atom with up and down electrons. So it's just, if you have metals with d orbitals, there are the way how they are occupied is tricky. And then d orbitals do have the same energy. They experience lifted degeneracy. Well, probably need to cover it in the course, but there are opportunities. So whatever we'll be doing in the class will be one-dimensional, but there is a way to connect activity that some of the helpers are doing for many dimensions and projecting into another dimension. So here are the two-dimensional wave packets in this little chunk of semiconductor. Not tired, not exhausted from the things that I told in the time. Okay. So once again, the most challenging information that will be offered in the rest of the course is that if one jumps between different potential energy surfaces, between different electronic states, then the forces imposed on interatomic on atoms and in interatomic distances will contract. One of the examples is if a little chunk of semiconductor is excited from ground to excited, there is a simultaneous change of angles and contraction of nearby atoms. It will look like jumping from potential with minimum at one place to potential with minimum at another place. This looks busy with a lot of details, but it is very doable with your background and skills. So one can look on the one-dimensional potential out of this multidimensional here and there and see how wave packet will go upon photo excitation. More about chemistry. So there are so-called dissociation reactions and photo dissociation. So the excited state potential surfaces can have non-conservative nature, which means instead, if you create an elongation, instead of returning into equilibrium, it will just run away. Dissipative potentials means no equilibrium. So some molecules are stable in the ground state, but become unstable if they are in the excited state. They excite and then atoms run away from each other, decompose. So originally it was a nice consolidated molecule, but if we excite as time passes by, pieces run away from each other. And this process can be modeled by intersecting potential, one which has a minimum, and another one is like 1 over R, the dissipated potential. So it was photo dissociation. One can try to look onto several potentials for photo association or photo polarization if group of precursors for synthesis merge together into a polymer. So polymerization from independent molecules into a chain. What is catalysis?
You catalyze something,
So, catalyze what?
a reaction,
Which means
to lower the activation energy or speed up the reaction.
I don't know what I'm doing here. You guys know what. So you can model select specific reaction and model just how we go by changing the height of the barrier, right? So one can work with very simple potentials that we have already considered in the lab. Just give specific values that would correspond to real reaction. What is difference between combustion and catalysis?
Combustion, you burn things.
But exothermic or endothermic?
The combustion is exothermic, catalysis is endothermic.
Well, probably there is an exothermic catalysis as well, but if it is spontaneous combustion, it means that there is a release of energy. The product is definitely more energetically favorable than a reactant, right? So if you just flip the relative heights of the reactant and product, it will correspond to combustion. So what can combust? What burns in real life?
Hydrogen.
Where do you burn hydrogen?
In a hydrogen cell.
Okay, fuel cell. It's like catalytic combustion. What else do you burn?
Spacecraft.
Excellent. You're a mind reader. Did you? Ah. So if there are some specific mixtures of fuel and oxidizers that react spontaneously without emission, and there is a big mess, right? Here. Yeah, it's hard to identify like this reactant. This is fuel. This is this is just water. This is product, but this one is nitric oxide, which is oxidizer. And as they are put together, there are several sets of reactions. But if one looks on individual reactions corresponding to this big mass, there is several chains of reactions that bring us from this reactive reactants to stable products, like nitrogen, water. And by going through them, there will be potential where product is lower than reactant. Right? So one can project such reaction sets of events onto one dimension, and then for such one dimension, one can establish a potential, compare with packet, and see how it will either reflect or pass through. This is something ready for big science and for it will be not only for the classic science, but something like this. It will be true research with a publication potential. If we are not comfortable with intersecting potential, something too complicated, one of the simplest things is just to look onto electron motion along a semiconductor where each atom corresponds to a little dip, or if there is an impurity or special atom, it could be lower dip, and one can give several examples of problems that are modeled by this sort of potentials. One of the typical things is p-n junction solar cell or photodiode or light. Oh, thank you. I need to wrap up. Another opportunity to look on this potential, there is a light and medium carbon nanotubes functionalized by the covalent doping. So if one puts specific, carbons from tube, and they can absorb light but not emit. If one puts specific dopings on them, they start to emit. And if one puts two dopings, the wave packet can move and reflect between these dopings. It's also problem with strong potential. Another example where I will be just much quicker on actual plasma. Another example where these one-dimensional potentials are really helpful is for donor and acceptor payload, like dye-sensitized solar cell. So here is atomistic model that the helper I provide to you, and here is one-dimensional projection where there is an atom, there is a dip, so it is flipped by negative degrees. Where there is no atom, it is a little higher. Where there is a specific group of atoms, like acceptor, it will be deeper. And it's motion of charge density from one species, one group, the donor, to another species, acceptor. There are several helpers in things like this. One of them is London Johnson, who took the class last year. So he will be happy to provide potential. So donor is perovskite semiconductor, acceptor is titanium dioxide. So the yellow part, which is electron density, migrates from this region of space to this region of space. And this is very modelable with one-dimensional potential. See, this looks like dual flows. And I think it is the last one. Bohr model, which is wrong but helpful for understanding. So the rigid rotor and Bohr model, which means the particle moves on circular orbits. Or it can move linearly with periodic boundary conditions. It is our simulation, so it reappears back. You have seen result of this project of some students in the past on our lecture number 2. Same thing as we do, but here is our x coordinate, right? With periodic boundary condition. Okay, lecture material. Applying the annihilation operator to a known wave function. We will assume that as in all eigenstates problems, the eigenvalue is non-zero. When eigenvalue is 0, it will be a problem to find ground state. Right? So we are expanding our unknown state as a superposition of all possible eigenstates of harmonic oscillator with unknown coefficients. Here and there is operator, wave function, eigenvalue, wave function. So it is an equation to solve for unknown expansion coefficients. The operator, annihilation operator, moves from ket to bra with lowering of index. So from k plus 1, it moves to k. And there is a factor at the front. So if we plug in the operator, we may practice our main skill to get rid of wave functions, to get rid of this brass. Right? So you can observe that here there is a bra from operator, and here is a ket from wave function. If this bra and ket meet each other, they will form orthogonality pattern, right? So this convolution will be Kronecker delta. It will be non-zero only if n equals k plus 1. right? No tricks. Nothing is cheesy. Just definitions. Plug in annihilation operator, unknown, bra and cat, give delta function. And if we do have delta function here and summation over and summation here, we see our favorite characters. Okay. What will happen? We will remove this part, remove one summation, and replace n, index n, to the index k, but not literally. We will replace n to the k plus 1. Okay. Or we can replace k to n minus 1, which is the same. Right? So everywhere where we had k, we put n minus 1. Where it was n, we keep it n. Where it was k, we put n minus 1. And then summation is over n. There were two summations, now there is one summation. Good? What do we see? We see equality. There is a series on the left and right. It's infinite number of terms. There are wave functions of harmonic oscillator, and there are functions in front of them. When two series are equal, when each term on left and right, corresponding term is corresponding index, equal on left and right. Yep. Is it comfortable to compare this stuff? Probably not. We would like to have the same index for n and n plus 1. And we can just rename indices consistently. We can either put n minus 1 here, there, and there, or we can change the summation variable on the right. We changed the summation on the right. So we consistently changed. It was n minus 1 here, and we changed it to n. It was n here, and we changed it to n plus 1. It was n here, and we changed it to n plus 1. So we just changed the labeling. It doesn't affect the mathematical part. Now we do have index n in the summation, not index, the eigenstate n and, on left and right. The eigenstates are the same, we use the same basis, and then this equality will be the same if the expansion coefficients are the same. So eigenvalue mu times this expansion coefficient C sub n, and coefficient at n plus 1 times this factor which increases as index increases. So how would you tell it from mathematical point of view? Do you, when there is a series and terms in series are not independent and depend on each other? If you are taking basic programming, or if you are taking math, you may have right word for this.
Recursive?
Yes. Did you hear this before? Recursive, yes. Think of that. N plus 1 for language. Recursive. Recursive. So recursion, which means if you can rewrite it in this way, so the next coefficient will depend on the previous one. So if you know coefficient C0, we will be able to find C1. If you know C1, we will be able to find C2, right? So there is a progression to find that. End of the meeting. Thank you for continue investing your time in the course. I hope very much that no one will decide to use opportunity to withdrawing because you are doing well with grades. And looking forward to see you on Friday. Tonight. Yes, good. 5 p.m.
Is computational chemistry just one big project?
It will be, first, there will be skills. It will be very similar to Wednesday labs, but the software will be easier for humans and harder for computers. It will be like running advanced software. There will be 2 lectures instead of 3, and there will be like equations and concepts of advanced subjects, but not at the level to derive equations and make homework, but only to explain what is going on inside the computer.
But then it's one big project. You work on just a big project, correct?
There will be a couple of presentations on showing basic skills, as we showed skills of using MATLAB. And then it will be one big project, yes.
So you said there's helpers for the presentation for
Yes,
this
yes. After you select project, I will provide a help.
Okay. And then are they just gonna like come to our lab or?
No, I will share email and then we exchange emails, and maybe it will just one email with some piece of data will be sufficient. Maybe you will meet.
Okay. Sounds good. Thank you.